Okay, so for this set of slides, we're going to talk about policy iteration, which is our second algorithm for Markov decision processes. Okay, so we talked about value iteration, and then as we saw, this algorithm is optimizing the value function, and then once we have a value function, then we can extract an induced policy simply by doing one more iteration, but instead writing down what are the actions that maximize that last iteration instead of writing down what is the new value, right? So effectively, right, we're working with value functions, but then it's just in the last step that we extract a policy. Now instead, we'd like to also optimize a policy directly, and then we can do this through another algorithm that's known as policy iteration. So that's the subject for this set of slides. Okay, so policy iteration, what it does is it alternates between two steps. We're going to have a first step where, given some policy, we're going to evaluate that policy through the value iteration algorithm that we saw, but for policy evaluation. And then given a policy, now we're going to do an improvement step. So this was similar to what we did in the last step of value iteration to extract a policy, but now we're going to do this to effectively just change our policy and then go back and evaluate it, right? And then after that, change again, and then evaluate and alternate between those two until convergence. Okay, so the policy iteration algorithm can be summarized as follows. So we start with any policy. We're going to see in a moment as well some theorems where it doesn't matter what policy we start with, the algorithm is going to converge to the optimal policy. So here you start with any policy, and then at every iteration, now you do two things. You evaluate the policy, and then you improve it. Right? So this is different from value iteration, where for value iteration, at every iteration we were doing one thing, which was simply to improve our estimate of the value function. Here, we alternate between evaluating a policy and then improving it. And then we'll simply stop when we have two consecutive policies that are identical. The intuition is that when I try to improve the policy, if it doesn't change, that means I haven't succeeded in improving it. And then at this point, I might as well stop because the algorithm will just be stuck. It won't be doing anything further. And then we'll prove in a moment that this will indeed be the optimal policy. Yeah?
Just to clarify, both this and value iteration assume we know state dynamics, right?
Yes. Yeah, so far we're still in the regime where we assume the dynamics of the environment, so the transition function is known, and we also know the reward function. But in the next set of slides, then we'll really get into reinforcement learning, and then we'll relax this assumption. Okay. Yes?
Sorry, and you said this will always converge, so we can't get stuck in a local minimum?
That's right. So yeah, this is beautiful because we do not get stuck into a local optimum. In fact, if you want to view this from an optimization perspective, we can write the optimization of a policy as a linear program, and then this is obviously convex, and then it will converge. Okay, so to illustrate the policy iteration algorithm, let's go back to the little toy example that we saw, where we have a company that might be in different states. Right, so it might be poor and unknown, or it might be poor and famous, or rich and unknown, and rich and famous. And now, if we apply policy iteration, where let's say we start with an arbitrary policy, where we simply advertise in every state. Okay, so perhaps this is our initial policy. We have no clue whether it's a good one or not. This is just what we pick to start. So if we evaluate that policy, where we simply advertise all the time, then we will get these values. And then at the next step, when we do the improvement, we're going to get a new policy that changes here to S for, that means saving. So for rich and famous, rich and unknown, poor and famous, in all these three states, it's going to save the money. and then it's going to continue to advertise in poor and unknown. So here we have a change of policy in that second iteration, and then if we evaluate it, these are the values that we would get. And then if we keep going and we do a third iteration, then at the third iteration we notice that the policy doesn't change. Okay, so it's going to remain save, 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 and advertise. Okay, and then because it remains the same, then obviously the value of the policy also remains the same. Okay, so this illustrates how the algorithm works. So for this very simple example, it effectively just took 3 iterations. In practice, obviously, it might take more iterations, but a nice property of policy iteration is that the number of iterations tends to be small. Okay, so in the worst case, it might be as many as value iteration, but in practice, it tends to be a lot smaller. Often on the order of 10 iterations is enough. Okay, so now let's talk about the properties of the algorithm. So I've got here a first lemma where I'm going to let Vn and Vn plus 1 to be 2 successive estimates of the value function for different policies. Okay, so here I've got a policy at time step n, another policy at time step n plus 1, and then their corresponding value functions, I'm going to assume that they're Vn and Vn plus 1. And here I'm in the context of policy iteration, so when I do policy iteration, right, there's a first step where I evaluate the policy, and then I can evaluate the policy exactly. Right? So then these value functions are not just estimates, they're in fact the exact value function of the corresponding policies. So what this lemma says is that at every iteration of policy iteration, we're going to change policy and necessarily improve the policy, or at least it won't get worse. So the policy will be at least as good. So this is what it means. Okay, so the proof is very simple. So here we have a specific policy, pi n. By definition, if we apply the value iteration algorithm an infinite number of times, then we would obtain an estimate here, and then it would be the same as Vn, which is, again, the true value for that policy. Now, we can compare that to applying H star, and then H star, if you recall, is the main difference between H star and H pi is that H star would select the action that maximizes the value, whereas H pi simply selects actions according to pi. So necessarily, if I select actions that are maximizing, then this has to be greater or equal than that. Okay? So we know this, and we also know that pi n plus 1 was obtained by selecting the action that maximizes. So when I apply H star, I effectively apply pi n plus 1. So here H star Vn is going to be equal to this expression, right? So this is the reward for that corresponds to this policy pi n plus 1, and it's greater or equal than Vn, right? So here I'm taking the first line, rewriting it in the third line, where I simply expanded this to correspond to this expression. Okay. Then I rearrange the terms. So here I want to isolate Vn. So I'm going to bring Vn on this side. And then after this, I can take the fact that Vn plus 1 is equal to this expression and also greater or equal than Vn to complete the proof. Okay. So very simple proof, and then here it shows that the value of the next policy after I do the policy improvement step is necessarily going to be higher. Therefore, this increases monotonically. Any questions regarding this? Yeah.
Is the optimal value function unique?
Yes, so the optimal value function is unique. Now, in terms of policies, the optimal policy, there might be several optimal policies, but they will all have the same optimal value function. Yeah. Okay, so we're now ready to prove that policy iteration will converge to the optimal policy pi star, and will also have a value function v star, and this will be achieved in finitely many iterations. Okay, and this is as long as S and A are finite. If you have continuous or infinitely many states or actions, then it's not as obvious, and it's not necessarily the case that it's going to be finite, but when those are finite, then the number of iterations is also going to be finite. Okay, so the proof is fairly simple again. So we know from lemma 1 that at every iteration we improve the value function. Now, we also know that if we have finitely many states and actions, then we have only finitely many policies that we could visit in the algorithm. And then at every step, I'm going to improve the policy, so I'm going to get a value function that's better. So I cannot visit the same policy more than once. So if I visit a policy a second time, then it means that I'm stuck, that I've converged. Okay, so then at the termination, this is when I will have the same policy twice. And then at that point, we can show that it satisfies Bellman's equation. Okay? So to convince yourself that this will converge in finitely many iterations, the main argument is that because A and S are finite, then we've got finitely many policies, and we never visit policies more than once. Right? And then for understanding that this will be necessarily the optimal policy and value function at the end, the key is that at the end, we end up with an equation that is precisely Bellman's equation. Yeah, because when the policy doesn't change, then the value doesn't change. And now you see we've got Vn on this side, Vn on that side, so that means we've got Bellman's equation. And Bellman's equation was used earlier to show that this is a sufficient condition for obtaining an optimal value function. Okay. Any questions regarding this? Yes?
I want to make sure, why is it the case that that one policy will not be visited like twice? Because I thought, for example, there could be like multiple policies to the optimal value function, right? So would it be the case like I will come up with policy A, and then because the value function is just greater or equal to, so I could also alternate to the policy B, which also has the optimal value, and then alternate between them.
Okay, yeah, you've got a good point here. So yeah, the question is, is it possible to cycle between a set of optimal policies, or at least a set of policies that have the same value? And I guess yes. Here, in theory, yes, this might happen. So I guess, okay, in the previous slide, when we talked about the algorithm, I guess what I should do is change this so that instead of verifying whenever we've got the same policy twice, I should change the termination condition to be that whenever you've got the same value function twice, then you stop. Because you might have several policies that have the same value function. So yes, this might allow you to cycle, but then they will all have the same value function. So then it would stop at that point. Yeah.
Still a continued problem. So would it be possible to, although it's not the optimal value function, but still like the same value function, different policies that share same value function that is not optimal?
Yeah, so it is possible to have several policies that are not optimal to have the same value function. But now, Right. Okay, I see. Because yeah, the way I described this, I just showed that it's monotonically increasing, but not strictly increasing. Right. So I guess we need a stronger theorem here. Let's see. Yeah. So here we should be able to prove a stronger statement than this, where it's greater. No, I guess no. It cannot be greater than or equal, because when you arrive at the optimal policy, then you cannot improve further. But I guess yeah, the point is that when you're still at a suboptimal policy, then you don't want to be in a situation where you just find something that's equal. Yeah, we'd have to. Okay, so I guess so this proof then is not complete. Right? So there's an argument. So that's a very good point. So there's an argument missing here to show that yeah, whenever it's suboptimal, we will necessarily be increasing the value and not just finding something that's the same. Yeah. Yes.
For the same reason, can we avoid the local optimal here?
So okay, here there is no local optimum because this is monotonically increasing, and then we. Well, okay, I have a proof that I guess is not complete, but still the theorem does hold, okay, where in the end you will converge to the optimal policy. So then, yeah, from that perspective, if you were getting stuck into a local optimum, then it would be a case where you're not at the optimal policy, and then you would think that there's no further improvement possible. Okay, but here, if there's an improvement possible, then this algorithm will find it. That's the key idea. Yeah. Okay, very good. Okay, so to summarize, so for value iteration, we've already seen that at each iteration, right, then the complexity was s squared times a, and then value iteration does take a large number of iterations, so the convergence is linear. Now, if we compare this to policy iteration, what we obtain instead is that now each iteration is going to have a complexity that's cubic in S, and also still we have a term of s squared times a, but we're going to require fewer iterations most of the time, and then the convergence rate is somewhere between linear and quadratic. So here, just to be clear, when I talk about convergence rate, quadratic is better than linear. Okay, so it might be a little counterintuitive, because if we think of complexity theory, typically we want an algorithm that has a complexity that is low. But then when we talk about convergence, we want to have a convergence rate that is high. Okay, so here quadratic is better. And then we saw in the example, our toy example, right, that it only took 3 iterations for policy iteration. And then if you recall from last week, when we talked about value iteration, then for that same toy example, right, I had many iterations on the slide, and it still had not converged. If you run it till convergence, or at least till you have a gap of just epsilon, which then gives you a bound of epsilon divided by 1 minus gamma, right? So for a very small epsilon, you might require hundreds, if not thousands of iterations, right? So in general, value iteration does require a lot more iterations, but on the other hand, the cost of each iteration is smaller, right? So here, the complexity is s squared, whereas here it's s cubed. So if we have a problem with lots of states, then this can be quite expensive, and now it's unclear which one of those 2 techniques is going to be the fastest, right? Because it really depends between the cost per iteration and the number of iterations. Okay, so given that we have this trade-off, right? So here, ideally, we would like to have a technique that has few iterations, as in policy iteration, but then a small cost per iteration, as in value iteration. So what we could do is, in fact, come up with some algorithm that is in between those 2 and is known as modified policy iteration. So what modified policy iteration does is essentially policy iteration, but then in order to reduce the cost per iteration, it will do a partial policy evaluation. Okay, so if you remember, what was expensive about policy iteration was the policy evaluation, because if you do it exactly, you're solving a system of linear equations, and solving a system of linear equations takes cubic time with respect to the dimensionality. So here that's essentially the number of states. But now maybe we don't have to evaluate the policy perfectly. Maybe we just need to get some rough estimate and then improve with respect to that estimate, or at least select some action that would be maximizing with respect to that estimate, and then obtain a new policy. So this is the modified policy iteration algorithm, right? So we essentially relax the first step or make it simpler by just evaluating partly or partially the policy. And then most of the time this will be fine, because most of the time you don't have to have exact values. At some point it becomes clear that there's some actions that are worse than others, and then when you do the policy improvement step, you'll be able to still improve the policy. Okay? So that's why this algorithm in practice will often beat both value iteration and policy iteration, because it essentially exploits the best of both worlds. Okay, so here's the full algorithm. So we start with some policy pi 0 and v0 for the value function. These two can be initialized to anything. Then you repeat the following steps where you alternate between evaluation, but now we don't do an exact evaluation. We're just going to be doing case steps of value iteration. So, but here in the context of policy evaluation, right? So just do k iterations. And then we have an estimate. It's not perfect, but what we're going to do is see if we can come up with better actions based on that estimate. Because the estimate is not perfect, then it's possible we won't come up with the best improvement, but most of the time it will still be very good. And then we simply repeat this, and then we can stop whenever the difference between the values is at most epsilon. Yeah?
Why we can initialize v0 to anything?
So yeah, we initialize it to anything, because what we'll do is, as a first step here, right, we're going to evaluate the policy. And then if you remember, this algorithm for policy evaluation doesn't matter where we start, right? So according to the contraction mapping lemma, right, then any difference will shrink, and then we can prove that it converges to the same estimate regardless of where we start from. Okay, so now in terms of convergence, turns out that we have the same convergence guarantees as value iteration. Right, so here, I'm not going to go through the proof. If you want, you can check it out in Puterman's book. So that would be section 6.5. It's actually a little more complex than one slide, okay? But it works in a very similar way as the proofs that we saw before. And what we can show is that when we stop with just a gap of epsilon between two iterations, then the difference between our last estimate and the optimal value function will again be epsilon divided by 1 minus gamma. And now if we want to induce a policy from this, right, so then when we do the improvement step, we're essentially computing a policy that's induced from Vn. So I'm going to call that V pi n. And then that one will have, in the worst case, a value that's 2 epsilon divided by 1 minus gamma. Okay? So here, yeah, you can see that because Vn is not a perfect estimate, right, when I do the policy improvement step, you see I might make things worse simply because it wasn't perfect, and that's how we go from epsilon to 2 epsilon. Okay? So in any case, yeah, these are the same guarantees as what we saw for value iteration. Okay, so now in terms of complexity, we've already talked about value iteration and policy iteration. Now if we write down what happens with modified policy iteration, then each iteration will have a complexity that is now square in S, but we're going to have to take into account how many steps K we do for policy evaluation. And generally speaking, this will be a lot smaller than the number of states. Right? So that's why the cost per iteration is usually going to be smaller than for policy iteration. And then in terms of iterations, well, in general, it's going to be more than policy iteration, but a lot less than value iteration. So it's going to be in between those two. Depending on what K we choose, right, then this will decide whether we're closer to policy iteration or closer to value iteration. And then so as a result, the convergence rate is somewhere between linear and quadratic. So in practice, this tends to be the fastest algorithm within those three, simply because in practice, often you can get away with just a few steps of policy evaluation, and then it will allow you to select a good improvement for the policy at the next step. Okay. Any questions regarding this? Yeah.
Just to clarify, what was the K?
K is the number of iterations that we do in policy evaluation. So if I just go back, here's the algorithm. So repeat K times this step. Yeah. Yes?
In that case, if we keep on repeating K, that case equal to infinity, that should be value iteration, right?
Okay, so yeah, if K goes to infinity, this would be in fact policy iteration, because if K goes to infinity, then we have here a perfect estimate of the value. So we're doing policy evaluation exactly, and then we're after that doing an improvement step. So K that's infinite is effectively policy iteration. And then if we have K that is 0, right, so this would be value iteration.
In value iteration, we don't change the policy.
So yeah, in value iteration, you're right. We never change the policy, but the reason is because we don't even record what the policy is. All we do is this step, right? So at every step, I'm going to have my max over actions, right, which implicitly changes what the policy is. It's just that I don't record it, right? So here, what I do is I record what is this new policy, right? And then after that, I would do an improvement step. But then, yeah, these are effectively the same. So that's why if K is 0, then we're just doing the improvement step, and that corresponds to value iteration that we saw. Yeah.
What makes the complexity different?
So what makes the complexity?
Between policy iteration and value iteration.
Okay, so let's go back to the slide for this. Okay, so for value iteration and policy iteration, yeah, the difference in complexity is when we look at these two different iterations, right? So this one has just this one line where we have the max over actions, the reward plus the transition times the value function, and it has this complexity, right? And then policy iteration has two steps in the iteration, and then so there's one step that corresponds to evaluating the policy exactly. That means solving a system of linear equations, and that's S cubed. And then there's the other improvement step, which is S squared times A. Yeah?
And do all of these three algorithms converge to the same optimal policy?
Yes, so all three algorithms converge to the same thing if you do enough iterations. I mean, in practice, so like this one, you would stop at some point and then induce a policy out of this. Same thing here. So those two, you might stop before you actually have the optimal policy. This one, because you really go from one policy to the next and so on, you would typically stop really when you have the optimal policy. Yeah?
But in value iteration, we also need the max over action.
Yeah, so we also have the max over action in value iteration. So that's why here there's a complexity that's with respect to the number of actions. Yeah.
The value of k cannot go infinite if the number of states are finite, right?
So I say that again, the number
The
of...
value of k cannot go infinite if k, the number of times you evaluate a policy.
Yeah, so
It can go infinite if
here...
states are finite.
Right, so yeah, can k go to infinity or not? That's a good question. Let's
Given
go...
that we have finite states.
Right, so yeah, so here, yeah, if we... yeah, so there's definitely only a finite number of policies. In this case, the trouble is I don't think we can guarantee that there's monotonic improvement necessarily in terms of the policies. Because you see, you evaluate a policy partly, so when you try to improve with respect to this partial evaluation, you might actually get into a worse policy. So yeah, we don't have the same type of monotonic improvement in terms of the policies. We have monotonic improvement in terms of the value estimates. Actually, no, not even. So I don't think we have a monotonic improvement for the value estimates either. So yeah, so that's why the proofs there are more complex. I didn't go through them, right? But they are in Puterman's book. And the key is that in the limit, yeah, you will converge still to the same thing. But here, I don't think we can necessarily guarantee that you will do a number of steps or that is bounded by the number of policies. You might revisit some policies. Yeah.
Can you go back to the slide for the policy iteration?
Okay.
I think here, as you evaluate Vn, the value only once. Right? So I think that's a special case for modified policy iteration with k equal to 1, not k equal to...
Oh, sorry. Okay, here, this is not a step of value iteration. So you'll notice that I've got Vn on this side and Vn on that side, right? So this is, think of this as a system of linear equations, right? And then I'm just applying, let's say, Gaussian elimination. Okay, so that's why this is not an iteration, right? It's solving a system of linear equations. Okay, and you can see the difference because when it's an iteration, I use the arrow, the left arrow, to indicate that whatever I compute on the right-hand side, I store it into the left-hand side, right? But here I've got equality, so what I'm really doing is simply solving this system of linear equations.
And according to the final slide, like it's equivalent to k equal to the size of states, right? So for policy iteration, if you
Oops, let's go back. Yeah, so
k to the size of states.
yeah, if k is equal to the number of states, then yeah, the complexity here would be the same.
Yeah, but how can you see it from the value?
This is just an empirical observation. Okay, so in practice, you will typically need, you can often get away with a k that is much smaller. So often you can get away with a k that is constant, in fact, like maybe 3 or 4 steps. The reason is because you can evaluate the policy for a couple of steps. Then when you improve the policy, let's go back to the algorithm. Yeah, so you see, I will do a few steps here that will improve Vn, right? Then after this, I do a policy improvement step where I do a max over A, right? So that keeps on improving my estimate Vn. So the way to think about this algorithm is in fact more like value iteration, where at every step, I have an improved estimate of the optimal value function. So even though here, I'm not evaluating this perfectly, I'm just doing a few steps, right? Then here I improve, then I get a new policy, and then when I try to evaluate the new policy, I already start with the estimate of the previous policy, so it's like a warm start, and then I can just do a few steps here, like maybe 3 or 4 steps, and then improve again, and so on. So that's why you can often pick a k that is very small, and then in fact, I mean, if k is 0, it corresponds to value iteration. If k is greater than 0, then you do these additional steps here, and then they don't hurt. You're just evaluating the policy, but then things will improve, so the value will improve gradually just based on that iteration here. Okay, very good. So yeah, this was a good set of questions. And we're done, so let's take a break.